Hi, I am Abubakar. I am a PhD candidate at University of California, Riverside. I will present our work on zero-shot slot filling. This work was done in a collaboration with Fouad Jamour and my PhD advisor, Professor Vagalis Aristides. Before I talk about zero-shot slot filling and our model, let us understand what slot filling is. When you interact with any conversational AI system, especially goal-oriented ones, such as Google Assistant, the system tries to fulfill your request. For the system to do that, it needs to extract your request parameters, or in other words, slot values. For example, if you say, I would like to book a table at 8 Immortals restaurant in San Francisco for 5:30 p.m. today for 6 people. 8 Immortals restaurant is the restaurant name. San Francisco is the name of the city where restaurant is located. 5:30 p.m. is the reservation time the user is requesting. Today is the reservation day. And 6 is the party size. Now we are ready to define slot filling. Slot filling is extracting parameter values from a natural language utterance. As you can see, this is a critical step in any goal-oriented dialogue system because without it, the system won't be able to understand the needs of the user. Let us get a bit formal now. Slot filling is usually formulated as sequence tagging or token classification task using IOB tagging scheme. Given a sequence of words X, which is our utterance, we want to give a tag for each word as follows. The first word of a slot value associated with a slot type is labeled as B-slot type, where B is for begin. The other words inside the same slot value are labeled as I-slot type, where I is for inside. Note that one utterance can have more than one slot values. And non-slot words are labeled as O, where O is for outside. In our example utterance, 8 gets the label B-restaurant name and Immortals and restaurant gets the label I-restaurant name. And this animation shows how each word in the example utterance is labeled for IOB tagging scheme. Although slot filling is a challenging task due to vast diversity of expression, supervised approaches have shown promising results for the task. However, supervised methods rely on the critical assumption that the training and test set are drawn from the same underlying distribution. For example, if the model is trained on a dataset that belongs to the restaurant domain, the test set should also come from the same domain, that is restaurant. And this is also true for the supervised models that are trained on multi-domain datasets. However, such models are likely to result in significantly poor performance when confronted with new domains that were never seen during training. In this case, the model would show poor performance in hotels, movies, ride-sharing domains. This setting puts an unsustainable requirement of having labeled training data for each new domain. This requirement is unsustainable because acquisition of labeled training data for each new domain is laborious and expensive. And that motivates our task of zero-shot slot filling. Zero-shot learning models promise to adapt to new unseen domains seamlessly, which is very critical for conversational AI systems to function effectively in real world. Let us now look at the challenges that face a slot filling model when confronted with utterances from a new domain. In this case, let us assume that we have a model that was trained on a restaurant domain, but our utterances after the deployment come from the ride-sharing domain. Let us look at the example utterance. Can you find a shared cab to 2042 University Avenue for 2 passengers? During training, the model has not seen any training example for slot type ride type, rider address, and number of seats. Although the model has seen similar slot type party size in restaurant domain, yet it is still challenging to detect slot value for number of seats in unseen ride-sharing domain because of the different context, which makes zero-shot slot filling task very challenging. To take on the challenge of the zero-shot slot filling task, we propose an end-to-end neural network called Leona that works in 3 steps. Step 1 leverages pre-trained NLP models to acquire domain-oblivious and context-aware features about the utterance words. These features are useful regardless of the domain and are readily available, which makes them very useful in zero-shot slot filling. Step 2 fine-tunes these semantically rich features and produces slot-independent tags. These slot-independent tags provide cues at a different granularity for the final step. Step 3 learns a generalizable context-aware similarity function between utterance words and those of the slot from seen domains and exploit the learned function in unseen domains. This step puts everything together and further contextualizes the representations for the final predictions. Now let us see each step in detail. Step 1 uses pre-trained NLP models such as POS and NER taggers and contextual word representations from pre-trained language models. Let us zoom into step 1. POS tags provide initial information on the possibility of a word being a slot value. For example, proper nouns are usually slot values. Similarly, NER taggers also provide information on specific entities. Although NER taggers provide only a few basic entity types, many, though not all, slot types can be mapped to these basic entities. Please remember that directly assigning these tags to some slot types based on some similarity function would produce very low recall. That's why we use these tags only as initial cues. Language models are pre-trained on huge corpus of text in unsupervised fashion and provide rich contextual representations for utterance words. POS tags, NER tags, and contextual word embeddings form very powerful initialization features for the slot filling task because these features do not depend on any domain and are readily available for unseen domains even. Step 2 uses these features to initialize the embedding layer. Embedding layer uses a two-layer highway network to combine these features. Then bidirectional LSTM network is used to capture temporal interactions between input words. And CRF layer is used to predict IOB tags irrespective of the slot type. Unlike previous work that uses these IOB tags to predict final slot types, we use these predictions as hints for next step. And these hints are a lot better than the ones we got from step 1. Step 3 uses slot-independent tags and utterance-encoded representations to predict slot-specific tags. Specifically, we use utterance and slot encodings to compute a similarity matrix, A, that captures similarity between utterance words and slot. Cell JK in matrix A is computed using this equation. Now let us parse this equation. H represents utterance encoding and H subscript colon J is the jth column vector of the utterance that essentially represents encoding of the jth word in the utterance. Similarly, U represents slot encoding and U subscript colon K represents the kth column vector of the slot encoding. And alpha is a trainable similarity function that can be thought of as a multi-layer perceptron that captures the similarity between jth utterance word and kth slot word. Similarly, the whole matrix A can be computed. Then contextualization layer employs bidirectional LSTM network to contextualize utterance encoding, IOB predictions, and similarity between utterance and slots. Then another CRF layer predicts tags for the given slot type. This step is repeated for every relevant slot, and their predictions are combined to have the final predictions for the utterance. To summarize, our proposed model Leona works in 3 steps. Step 1 acquires domain oblivious features. Step 2 fine-tunes these features and produces slot-independent tags. And finally, step 3 employs a similarity function and generates slot-specific tags. To validate that our proposed model works well, we trained on all the domains in a dataset except one that is unseen during training and is used for testing. I will elaborate on this in a second. And used F1 score as the main metric. We experimented on 4 different public datasets, including ACD, which has over 188k utterances across 20 domains and 240 slots. Here I am presenting results of our model and the best competing model from ACL 2020 on a subset of domains from SGD dataset. Before you read these numbers, let us understand what they mean in more detail. To elaborate on the setup, when we test on buses domain, the model is trained on everything other than buses domain, the zero-shot setting. When we test on calendar domain, the model is trained on everything other than calendar domain. And this step is repeated for every single domain: events, flights, music, and so on. The main takeaway from this result is that our model outperforms the other state-of-the-art models on every single domain. And this performance is consistent across all other datasets in a wide range of experimental setups. We have several other interesting experimental setups and their analysis in our paper, such as results on seen and unseen slot types, and varying the percentages of seen and unseen domains. And we train models on one full dataset and test on all other datasets. But for these results, you will need to see the paper. With the availability of the powerful pre-trained NLP models, it is highly critical to show whether our custom layers are doing something useful or not. To highlight the role of each step in our model, I present the results of Ablation Study conducted on our model on multi-WOS and SGD datasets, which are challenging datasets. If we just use step 2 from our model and assign slot-independent tags to the nearest slot type based on some similarity function such as cosine similarity, we get results that are as good as the previous method. However, if we also incorporate step 1, we get improvement on all the dataset that is enough to get better than the previous state of the art. Similarly, if we just use step 3 of our model, that is almost as good as we had combined step 1 and step 2. But can we do better? Yes. If we employ step 2 and step 3, we see a significant improvement which highlights that cues from step 2 are critical. Can we do even better? Once more, yes. When all the components are put together, we can observe the best results, which is consistent across all the dataset, every single domain. To summarize, our model Leona works in 3 steps. Step 1 employs pre-trained NLP models to acquire domain-oblivious features. Step 2 fine-tunes these features and predicts slot-independent tags. Step 3 exploits a learned similarity function to predict slot-specific tags. And our proposed approach outperforms existing methods consistently on all 4 public datasets in a wide range of experimental setups. We are further exploring whether pre-trained NLP models can boost the performance of other zero-shot tasks. All the related code and datasets are available on this GitHub repository. With that, I conclude my talk and looking forward to the QA session.